All right, here's one more example from class 17. This is example 4, and we're doing rigid body kinematics and acceleration. All right, so here's another 4-bar mechanism right here. And at this point, this bar right here is rotating at 5 radians per second at a constant, right? So there's no angular acceleration. And we want to find the angular acceleration of this long member BDE and find the acceleration at point E. Okay, so some dimensions that would be helpful to us right here. We find that they only gave us the horizontal and horizontal and vertical dimensions. So if we take the square root of 90 squared plus 225 squared, we find that this is 242.3 millimeters. And we notice that it's going to be the same up to here, so this total length up here when we add them together is 484.6. And if we take the inverse tangent of 90 over 225, we get an angle of 21.80 degrees, and we're going to need that. So I start from the beginning. I do a velocity analysis, velocity and acceleration analysis of link AB. And I'll leave out some of the in-between steps here, but we find out that VB is just simply going to be 5 radians per second times 90 millimeters, so we get 450 millimeters per second. That's going 5 radians per second on there. We can also, at this time, find the acceleration right here, the normal acceleration of B, which is also the entire acceleration of B. Let's see, this is the normal acceleration. And I'll just write this way right here. So that's going to be omega squared, which is 5, times that 90, which is going to give us 2,250, that's a comma, not a, millimeters per second squared. Okay, now if we move on to the next part right here, that would be BDE for velocity analysis. Let's take a look and see what's going to happen here. We place that velocity VB right on here. But what's the velocity going to be of D? Well, or what direction is it going to be in? We know that it has to be horizontal, right? Because this thing is in the vertical position. It's going to rotate, and so it's going to go along that line. These are parallel lines. Is there any way that VB could not be, and with parallel lines we know that it's going to have an infinite that we're going to have with those parallel lines, or let me put it this way, the line that we would draw through here, if we were looking for the instantaneous center of rotation, the line that we draw, those would be parallel to each other as well as the velocity vectors. Our conclusion is that the velocity of D has to equal the velocity of B at this point right here in this orientation, so that omega BDE is equal to 0. So it's not rotating. We've found another example, unfortunately, where that omega is 0. Some interesting things are going to happen from here, though, so that's the value of this problem. Now we take a look at link CD. Right. And so we just march through this thing. And what we know, we've already found what the velocity of D is going to be 450 millimeters per second. So we can find the omega of CD is going to be equal to the velocity of D divided by the length of CD, right? So, but it's 180 longer, so we can kind of see where this is going. At 450 divided by 180, and we get 2.5 radians per second. All right, so it's got 1/2 of the angular velocity of the smaller link right there. We can also find the acceleration, but only the normal acceleration. Okay, so here's an important thing. We have to think our way through this, that the acceleration here at D is not the same, is not going to only be the normal acceleration, right? There's also going to be a tangential one, which we don't know. We'll put that there. And by the way, that's going to be the x direction. It's in the x direction if there is a tangential one, and we will see that there is going to be an alpha CD that's in existence. We don't need to find it. We weren't asked for it, but that would be something that we could be asked. The acceleration in the normal direction at D is also going to be the y component of this right here, and it's going to be pointing downwards towards the pivot point. So that's going to be the 2.5 radians per second squared times the 180. That's the length of CD. And what we end up with is 1,125 millimeters per second squared, right? The math works out because it's twice the length and 1/2 of the angular velocity. It just turns out to be ends up being 1/2 of the normal acceleration. Now that we have that information, we can attack BDE. So I'll start a new slide right here, and we'll draw this all in carefully. Right. So we do the 3 diagrams. And we apply what we know. We have the acceleration of B right here. We have the acceleration of D in the y direction. We don't know the acceleration of D in the x direction. I'm going to go ahead and use this diagram for well, we'll leave that. We'll see that in a second. And so we'll take the acceleration of B right here, because we know B, we're going to use that as the reference right here. So right below, we would write, we're going to do it, the acceleration of D is going to be equal to the acceleration of B plus the acceleration of D with respect to B tangentially plus the acceleration of D with respect to B in the normal direction. So continuing on with this, now we're going to pivot. We'll pivot about B and then draw, we'll make these the darker red. And we're going to have a normal, a tangential right here. So this is the acceleration of D with respect to B in the tangential direction, and this is the acceleration of D with respect to B in the normal direction. But something we know, and something we know about the normal direction already, it's going to be 0, because we'll note from the previous slide, because this was 0. So we don't have an omega to omega squared times that length right there. But we're going to have, we will find that we have an alpha, and I assumed it of the B, D, E. I assumed it in the clockwise, the counterclockwise direction, the positive direction. Something to be on the lookout for are the angles of this. That angle right there is going to be our 21.80 degrees. That's formed from vertical right there for the tangential. And you know, if we did need to know it for the normal, it would be that angle right there. All right. So our strategy for finding what's taking place in this is to use the stuff that we do know, right? So we could take it in the y direction, right? So we take in the y direction, because we know information here. We have the acceleration of d in the y direction. We already got that as a negative 1,125. Right? Once again, that's a comma, not a period. And it's going to be equal to what's happening at b right here, and that's going to be the negative 2,250. And we're going to, the way I have it drawn for the tangential is going to be in the upwards direction. So it's positive, and that's going to be alpha BDE times the length in between D and B, which is 242.3, but it's only a portion of it. It's going to be the cosine of 21.80, and then we'll put in a 0 right here to represent this contribution. From this, we're able to find BDE is equal to 5.00, and because of my round off error, I got a 1 right there. Right, so here's a case where you'll get if you dropped I used 4 sig figs, but that still wasn't quite enough. If you go further, you'll find that that's actually equal to exactly 5 radians per second squared. We don't have to find the x direction here. We weren't asked that, so we won't. Let's save some time. Use it for something else. Now let's do E. Now I'm going to go ahead and try to save some time here for myself and use the same figure. So AE in the x direction and AE in the y direction, and I drew them both as positive up there onto this diagram. I again add in AB because it's the one that I know. And then up here, let me make some room for myself. I have AE with respect to B in the tangential direction, and AE with respect to B in the normal direction, which again is going to be 0 because there is no angular velocity. So I take a look at the x direction. Well, let me write out the equation that we're basing everything on here up above, right? So that's going to be AE as a vector is equal to AB plus AE with respect to B, tangential plus AE with respect to B in the normal. And then I go for the x direction first, and I find AE x, right? So I'm just looking at there, is going to be equal to AB in the x direction is going to be 0, and then let me take a look, zoom in right up here. I'm not zooming in, but I'll just remember that that right there was the 21.80 up there. So we're going to have, and it's going to be negative, actually. It's going to be in the negative direction, right? So that's pointing to the left, that component. So it's going to be minus 5 point, and I'm going to pretend like that one was there because that's what my calculator said. And the distance, that total distance, remember that was 484.6, 484.6, and it's only going to be the sine of 21.80, and what I end up getting is a negative 900 millimeters per second squared. So it's to the left. And then in the y direction, B, let's see, we're looking at this diagram. We see that B is going downwards. So it's and it was equal to negative 2,250, right? And then we take a look at the tangential up here, right up here, and we see that it's going to be upward, so it's positive 5.001, 484.6, and now it's the cosine of 21.80, and we get the surprising result that it equals to 0. But it actually will have some change. And by the way, this 900 actually would have some values in there. In fact, I think I got lazy on my page, but if I use that 5.001 from up above and 484.6, multiply it, and then let's do the, wait a minute, I can reuse that, so hit that again, and 21.8, and the sine of that times, actually I do get the 900, okay, so that's good. But if I were to do this other one and take the 21.8, take the cosine, multiply it, okay, yeah, I do get the 0. Okay, so that did work out, even though I had that extra little 1 right in there. Everything worked out, and I got actually those numbers if I round off to there. So I actually do get 0.000, 0.000. Okay. So the answer to the question was the BDE was equal to 5 radians per second, and counterclockwise, and the acceleration of E is equal to 900 millimeters per second squared, all horizontally. Now, anytime I get a weird answer like that, I want to go back and try to see how that could possibly be, or get some kind of confirmation. So I have the ability to, so I went ahead and did it, to run a SolidWorks simulation on this. So is that actually going to show up that way? Okay, that's interesting. Huh. Okay, so here is this part right here. I have made an assembly and mimicked this thing, and then I set use the SolidWorks motion analysis, right? This is an add-on. There's animation and basic motion, but motion analysis will actually let you do kinematics and some kinetics. I'm not very good at the kinetics part of it, but I hope to improve on that soon. Anyway, so I can run this simulation right here, and I have it so that I've traced this path, and I've also analyzed and I let it go for like 5 seconds right here. I input this, by the way, that has to be RPM, so I converted that 5 radians per second into 47.75, and I'm showing it to you at a slower rate, right? So it's slowing the thing down so that you could see. And I've done this thing where I put a little a point on the end right there so that we could track it, so they could see the path that it makes. These are called coupler curves, by the way, in mechanisms class. And I've plotted that point as well, the acceleration in both the x direction right here and the y direction. SolidWorks has this is really kind of annoying. The tables that they display right here are the charts, the plots. You can't control these. At least I have never figured it out, or if I did figure it out, I forgot it. The grids right here. So even when you superimpose them on there, they use 2 separate grids, so it doesn't make a lot of sense. So what we could do though is you can actually click on these plots and export them to a spreadsheet, and so that's what I did. And I did them for both, and then I copied one on top of another. I opened up a column right here. I wish I could move that stupid thing. And what I did right in here is I took that 47.75, divided by 60, so now it's revolutions per second, and I multiplied it by this time. So what this column now represents is the really kind of like the percentage of a revolution. So right here is 1 revolution, right? Just right in between there. So this is like a 1.25 seconds, 1.267 seconds. Oh, and I should mention that when I solved this, I could choose the number of frames per second, which actually means the number of calculated points. Why won't that come back up? Yeah, so I was able to choose what those were because I didn't like the discretization with the, I think it defaulted to 25 frames per second. I increased it to 60 frames per second. If you just ramp that up really high, it's going to bog down the machine. So anyway, let's see. It's not letting me jump to things I want to go to. Why are you being like that? All right. There you go. So I've plotted this, and I only plotted like a portion of the 2 things. So here is, I believe this is going to be right here. This is the y direction right there, and you can see that it's a very small, it's a pretty small number, 0.0947, and then you could see that for in the x direction I have 9. That's actually because I didn't realize it when I was making the assembly, but you can see the positive x is to the left as part of this. So actually the way they have it drawn right here, I actually have it backwards right here onto the thing on accident. But you can from this you can confirm, you can confirm that yes, it's the correct value, 900 millimeters per second, with some change in there because it's imperfect. And that's the starting one. So the reason why I plotted them for some more down here is like right here you could see when I think yeah, like right there, that point right there is once again where the where you're rotating, where we get another revolution right here. So it's like right here, and you could see that you know, we're getting to that same point right there. If we could we get close enough. Bottom line, we can confirm, and now we believe with a little bit more certainty that this was the results that we calculated by hand. All right, so that took 24 minutes, but the rest stuff was kind of add-on things at the end. I don't know if anyone's actually going to be listening to the 4th example of Class 17, but if you've made it this far, congratulations, you get some guitar. If I could find a guitar pick somewhere. Oh, No guitar pick. Oh, there you are. There's a guitar pick. And I have a Les Paul out. Let's see. I think I have the amp simulator still on a clean tone. It's not a very good sound in there. Well, I guess the tone knob was down. It's a lot of tune. Anyway, so wasted enough of your time. I hope you're doing well. Thanks for listening.